Energy. We all use it every day. But where does it come from? It's released by fire. It's even held by running water. And even wind. Some power plants use coal, and others can use nuclear energy.
What can nuclear energy do for us? Well, nuclear power plants generate electricity. Nuclear power plants operate similarly to how fossil fuel plants work. The only difference between nuclear plants and a fossil fuel plant is the fuel used. In traditional power plants, the burning of coal or other fossil fuels is what is used to heat water, which turns turbines and generates electricity. But when coal is burned, gases like sulfur dioxide and carbon dioxide are released into the atmosphere. Having too much carbon dioxide in the atmosphere is bad because it collects and forms an insulating layer in the atmosphere, and when heat comes from the sun's rays, the heat gets trapped inside the atmosphere, which is a major contributor to climate change, which has bad effects on our ecosystem like the melting of the Arctic glaciers. In nuclear plants, a similar idea is used, but instead of using coal or fossil fuels, nuclear plants use a different kind of fuel that is better for the environment. So, what exactly is the fuel in nuclear power plants? The fuel is uranium-235. It is made in small, round fuel pellets. Did you know that just one uranium pellet, less than an inch long, can produce the same amount of energy as a ton of coal? These pellets are placed end to end into rods that are over 12 feet long, and over 200 of these rods are grouped into what is known as the fuel assembly. In a nuclear power plant, all these fuel rods are undergoing a nuclear reaction that releases a lot of heat. Water is in the same chamber as the fuel rods, and this water gets superheated, and a pressurizer is used to keep the water from boiling so that instead of just turning into steam, it goes through tubes which, by contact, heat water in a separate container, which turns into steam, and that steam turns turbines, which generates electricity. This generated electricity is then sent to your city and is used to power your homes. Then, the steam is condensed by another separate water chamber that cools down the steam, and the process repeats. It is important to note that the water that comes into contact with the uranium never comes into contact with the water that is in the generators. So the water gets safely recycled and reused in the process, which is also eco-friendly.
Now, let's take a peek into the force behind it all. Nuclear energy.
What exactly is the chemistry of nuclear energy on an atomic level? You probably all know that atoms of any element are composed of protons and neutrons in the nucleus, held together by a strong nuclear force, and electrons surrounding this nucleus in a cloud, held to the nucleus by an electrostatic force. The number of protons for a particular element always has to be the same. For example, helium always has 2 protons. Atoms don't always have the same number of neutrons, given the isotopes' different masses, and these different numbers are what we call isotopes. Every atom has an isotope that is most common in nature, while others are not very common, but can still make a difference in how these atoms sometimes react. Some isotopes are stable, such as the main isotopes of chlorine, chlorine-35 and chlorine-37, but many isotopes are unstable and may be radioactive due to what is called radioactive decay. Atoms of this kind were discovered by Henri Becquerel in 1896 after he noticed glass became distorted when exposed to uranium, which meant they had to be exposed to some type of rays. In 1899, Ernest Rutherford discovered that uranium emitted 3 types of radiation: alpha, which emits the nucleus of a helium atom, beta, which emits high-speed electrons, and gamma, which emit high-energy photons. The gamma particles have the greatest effect on radiation strength, and lead is needed to stop them, while a sheet of paper is capable of stopping alpha rays. Each isotope has its own half-life, which is the time required for half the atoms to decay. The half-life of uranium-238 is 4.5 billion years. Carbon-14 is 5,730 years, making it useful to date organic matter. Fusion is the process where 2 nuclei come together to form one nucleus, such as 2 hydrogen atoms coming together to form a helium atom. E equals mc squared shows why this is a high-energy producing reaction. Fission is the opposite of fusion. 1 atom splits into 2. Large energies are given off because the initial nucleus is heavier than any of the resulting nuclei. Fission is typically harvested as power for us to use by tightly controlling this reaction, while fusion is used in nuclear weapons without controlling the reaction, causing a major explosion.
Now that you know a little bit about how a nuclear power plant works and the chemistry behind nuclear energy, let's take a look into some drawbacks. One concern with nuclear energy is nuclear waste. 55 million gallons of nuclear waste is made every year. The most dangerous nuclear energy waste is extremely radioactive, which just means that it's unstable and is decaying and emitting those previously mentioned alpha, beta, and gamma rays. Although this is a lot of waste to handle, means of storing it safely have already been designed. Another drawback of nuclear energy is radiation. Radioactive waste from nuclear power plants and the plants themselves can emit radiation. Again, radiation is basically particles being shot off from atoms at high speeds, some more dangerous than others. Although radiation can be dangerous, it is really just a numbers game. Everyone is hit by 15,000 radiation particles per second, meaning 500 billion per year and 40 trillion over a lifetime, all just from naturally occurring sources. To explain further, a typical X-ray in the doctor's office hits you with over 1 trillion particles of radiation. The probability of one of these particles causing enough damage to cells and their DNA to cause cancer is 1 in 30 quadrillion. Many of the highly publicized incidents, such as radioactive waste spills, really have the equivalent amount of radiation you just get by traveling to a state like Utah or Colorado for 5 days, where there is higher uranium content in the soil, and the higher altitude protects people less from radiation from cosmic rays. The point is, radiation can be dangerous, but most of the time it is much less dangerous than many things we do in our everyday lives.